Welcome to The Explainer. Today, we are embarking on a session I absolutely love to call the archaeological dig. We are taking a deep, strategic dive into Cambridge computer science exam strategy, and we are putting a massive magnifying glass on the 9618 assembly language instruction set. We are going to decode the exact instructions, LDM, LDD, LDI, LDX, and LDR, by looking directly through the eyes of the principal examiner. Imagine this exact process as an archaeological dig. You can't just scrape the surface. You have to meticulously uncover the hidden clues embedded in the exam question, layer by layer, to reveal the perfect maximum mark answer. Now, before we really get into the weeds, I want you to picture two very typical computer science students. Let's call them Alex and Sam. Now, Alex is that student who overloads every single answer with raw computer science facts. Alex memorizes the textbook cover to cover, but completely lacks analytical depth. When asked to evaluate an assembly instruction, Alex just regurgitates a dictionary definition. Then we have Sam. Sam's biggest enemy is the clock. Sam rushes, completely misses the specific requirements of the command words in the prompt, and just scribbles down a final calculation without showing any logical steps. Today, we are going to look at their flawed approaches, and we're going to entirely transform how you handle these exact same papers. Whether you are building your foundational logic in IGCSE courses like 0417, 0478, 0983, 0984, or O-Level 2210, all the way up to our main focus today, the Advanced A-Level 9618 syllabus, the core principles of decoding remain exactly the same. Let's get to work. We are kicking things off with a very direct, somewhat harsh warning pulled straight from a senior examiner's report. They literally state that this instruction set is one of the most misunderstood areas in all of computer science. This perfectly captures why students like Alex and Sam consistently drop multiple grade boundaries here. Mastering this highly specific instruction set requires a massive mental shift. You have to move away from rote memorization and step into true analytical depth. You see, you really cannot just memorize what these letters stand for and expect to pass. You can memorize that LDM is for immediate addressing, LDD is for direct addressing, LDI stands for indirect, LDX is for indexed, and LDR is for register loading. But guess what? If you try to just memorize those basic definitions, the moment Cambridge throws a completely unfamiliar system architecture or a massive complex trace table at you, that rote memorization completely shatters. You'll freeze. The examiner is explicitly telling us right here that this is a conceptual trap designed to catch out superficial learning. To actually conquer this section of the 9618 paper, you must fundamentally understand the why and the how behind memory access at the hardware level, not just the basic what. So here is our strategic playbook for today's session. First, decoding assembly language. Second, the procedural framework. Third, securing essential method marks. Fourth, top 3 examiner warnings. And finally, advanced evaluative thinking. Let's jump right into the first step. Section 1 is all about decoding assembly language, where we start finding the hidden clues within the core concepts. To overcome the massive challenge of mixing up these very similar-looking instructions, top computer science experts recommend using what we call the visual story method. This is a framework to anchor each command to a highly memorable, real-world sequence. Instead of staring blankly at a textbook, I want you to imagine this right now. LDM is load immediate. Picture a text message popping up on your phone screen. The data you need is immediately right there in the instruction itself. You don't have to go anywhere else to find it. Next, we have LDD, which is load direct. Picture walking directly to a very specific house address. The instruction gives you the exact, explicit memory address where your required data lives. Then we have LDI, load indirect. Think of this as a treasure hunt. You go to a house address, but instead of finding the actual data, you find a note pointing you to another address. It is a 2-step memory fetch process. Next up is LDX, load indexed. Imagine a massive apartment building. You have a base address, which is the front door of the building itself, but you desperately need an index, like a specific apartment number, to find the specific data. You physically add the base and the index register together. Finally, LDR is load to register, which is simply moving a box directly into a specific room. By visualizing these commands in this way, you build a bulletproof mental framework. Now, knowing the story is only half the battle. How do you write it down on the exam? This is where the PEEL framework comes in. Point, evidence, explanation, link. Top students structure every written assembly answer using PEEL to guarantee they hit all assessment objectives. Now, before we continue to exactly how to apply that framework, subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving right along to Section 2, the procedural framework, executing the standardized sequence.
Whenever you are faced with complex algorithmic challenges, Cambridge examiners fully expect you to apply these 4 core pillars: decomposition, data structure selection, efficient implementation, and rigorous testing. It is incredibly common for a student like Sam to look at a 20-line assembly language program, completely panic, and try to process the entire script simultaneously. But doing that entirely violates the very first pillar, decomposition. You absolutely must break the problem down step by step, analyzing just one single instruction and one single register change at a time, nothing more. Then we move to data structures. Let's say you're dealing with a one-dimensional array. If that's the case, you should instinctively, anticipate seeing the LDX, load indexed instruction pop up. Why? Because index addressing is specifically designed at the hardware level to iterate efficiently through arrays. That is the exact kind of high-level cross-topic connection the principal examiners are practically begging candidates to make. Implementation and testing involve executing that precise logic meticulously on your paper. So let's look at a standardized sequence next that absolutely forces you to apply these 4 pillars under the intense pressure of a real exam.
You must tackle every single assembly problem using this exact 5-step standardized sequence. I call this the computer science success blueprint. It ensures you extract the right data and draw evidence-based conclusions every single time. Let's conceptually run a 60-second rewrite challenge right now to see how an elite answer compares to a flawed one. A rushed student, like Sam, might just scribble down a final hex value for an accumulator, get the math slightly wrong, and earn 0 marks out of 5. But an elite student uses the blueprint. Step 1. Identify key elements. They take their pen and actually circle the command word. Is it LDI or LDD? Step 2. Apply relevant principles. They instantly recall our visual story method. It's LDI, so I know this is a 2-step indirect memory fetch. Step 3. Execute analysis with clear working. They draw a mini trace table right there in the margins of the exam paper. Step 4. Verify results. They double-check the hex to binary conversion. Step 5. Present in appropriate format. They write out the register contents exactly as the prompt requested, filling in the formal trace table flawlessly. Slowing your brain down to force it through these 5 exact steps guarantees high-level accuracy.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into Section 3, Securing Essential Method Marks. Now we have arrived at one of the single most critical insights of this entire explainer, understanding exactly how to secure those incredibly vital method marks. The method mark strategy is your ultimate bulletproof safety net. Listen to me closely. Examiners are actively, desperately looking for reasons to reward your systematic processing, regardless of a final binary calculation error. Let me paint a very realistic picture for you. You're 90 minutes into a grueling paper. Your brain is fatigued. You are tracing an LDX command. You correctly add the index register to the base address, you fetch the correct data from memory, and then you have to perform an addition operation in the accumulator. You do all the computer science logic absolutely perfectly. But in a brief moment of mathematical fatigue, you write that 1 + 1 = 1 in binary, completely forgetting to carry the bit. Your final answer sitting in the accumulator is totally wrong. If you were like Sam and you just wrote that final answer down in the box, you get a 0. It's a disaster. But if you showed the trace, if you showed the intermediate value loaded from the index address right there on the page, you get the method marks. The examiner sees your algorithmic thinking. They see you applied the correct assembly rules, and they give you the points anyway. As you can see clearly on this comparison, just writing down a final result only is going to cost you dearly. It demonstrates absolutely 0 proof of logical reasoning. By contrast, systematic processing guarantees you pick up partial marks. Think of this like a visual data scan challenge. If you look at a massive trace table, the core trend you should see is not just final numbers, but a story of data moving from register to register. The examiner's official mark scheme explicitly features columns labeled M1 or Method 1. These specific points are given purely for the attempt using the correct logical pathway. By using clear notation, like physically drawing arrows between memory addresses in your working out space, you tangibly prove your analytical depth. You make it incredibly easy for the examiner to justify giving you points. Remember, the examiner wants to give you marks, but you have to provide the physical evidence on the paper for them to do so. Show them the journey, not just the destination.
Moving into Section 4, we are going to look at the top 3 examiner warnings, specifically highlighting common pitfalls taken directly from the principal examiner reports.
There are exactly 3 major traps that consistently, year after year, trip up Cambridge computer science students when they are working with this specific instruction set. I want to play a game of Find the Flaw with you right now. If you are scanning a complex scenario, you have to be hunting for these traps before you even start calculating. So, what are the 3 fatal errors that students like Alex and Sam make over and over again? Let's reveal exactly what they are straight from the principal examiner's desk so you never make them yourself. To protect your grade, you must rigorously check for overflow, understand boundary conditions, and always anchor your answer to the specific context of the prompt. Let's do a Find the Flaw challenge. Listen to this commonly flawed student paragraph. The program uses LDA to load the value 250 into the accumulator. Then it adds 10, so the new value is 260. Did you spot the massive flaw? The flaw is completely ignoring boundary conditions and overflow. If that accumulator is an 8-bit register, the absolute maximum unsigned value it can hold is 255. Adding 10 to 250 causes a hard overflow error. The value isn't 260, the register wraps around or flags an overflow. Missing this happens when you treat the exam like basic arithmetic instead of computer architecture. The third trap is generic answers. This is Alex's specialty. When the question asks why LDX is used in a specific robotic motor control program, simply writing LDX is indexed addressing is far too generic. A top-tier context-specific Peel paragraph would be: Point, LDX is used to iterate efficiently. Evidence, it adds the index to the base address. Explanation, this allows the program to sequentially access the temperature readings of the motor stored in an array. Link, this avoids writing a brand new instruction for every single reading, saving memory in the robotic system. See the difference? Context is absolutely king. Finally, let's step into Section 5, Advanced Evaluative Thinking. This is exactly how you bridge the gap from average to top marks. The Cambridge Assessment Framework heavily penalizes superficial breadth. Relying on basic definitions without context gets you nowhere. Instead, they demand analytical depth, justifying decisions, analyzing trade-offs, and demonstrating cross-topic connections. This is where our 3 rules for top marks come into play. 1. Command word decoding. 2. Peel framework application. And 3. Time management matrix. How do you move from superficial breadth to true analytical depth? Well, superficial breadth is simply saying LDI is indirect addressing and takes longer. Analytical depth looks entirely different. It looks like this. While LDM provides the fastest execution because the operand is embedded within the instruction itself, its strict limitation is that the data is hard-coded and cannot change during runtime. Therefore, in this dynamic sensor system, LDI is necessary despite the slower 2-step memory fetch because it allows the base address of the sensor data to be updated dynamically in memory as conditions change. Do you see the massive difference there? We analyze a direct trade-off between speed and flexibility, and we justify the architectural decision. That is what secures the maximum marks on the paper. Furthermore, when an examiner's command word asks for an evaluation of alternatives, you must explicitly detail both the similarities and the differences to draw a valid conclusion. The crucial strategy here is using comparative connectives. You need to use words like whereas, conversely, similarly, and in contrast. If an exam prompt asks you to compare LDD and LDI, do not just write one paragraph about LDD and then a totally separate paragraph about LDI and expect the examiner to figure out the differences. You must integrate them. For example, both LDD and LDI require accessing main memory, which is inherently slower than immediate addressing. However, whereas LDD directly fetches the operand from the provided address in one cycle, LDI requires a second memory cycle to resolve the pointer to the actual data. Consequently, LDD is vastly more efficient for static variables, while LDI is essential for utilizing pointers and dynamic data structures. You are actively building a compelling story that connects ideas and shows deep structural relationships. You aren't just reciting facts, you are thinking like a computer scientist. So, as you prepare to tackle your next past paper, ask yourself, how will you systematically apply the method mark strategy and cross-topic connections to your next unfamiliar assembly language context? The tools are now completely in your hands. The examiner's playbook is wide open. Students who implement these exact computer science strategies see an average improvement of 2 full grade boundaries, but that only happens if they practice consistently with our weekly sessions. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.